Assalamu alaikum students. Today we shall continue from the NMR, and we had discussed the basics of the NMR spectroscopy in our previous lecture. Now we'll see how the carbon-13 NMR basically works. So in carbon-13 NMR, the element which we are going to deal is the carbon-13, or element is carbon and the isotope is 13. Because we said that in previous case, in our previous lecture, that those elements can be detected in the NMR which have the odd number of the nucleon number, which have odd values of the nucleon number. So carbon-13 has odd number of the nucleons. Now carbon-13 will be present in the organic compounds, and that could be used to find how the peaks are formed. So in NMR spectroscopy, the peaks of the carbon-13 will be visible on the graph, and those carbons will be present in the molecules. So carbon-13 will be used to find the structure of the organic compound, because this is the spectroscopy which will indicate that how the structure is basically connected, how one element is connected with the other element, how one group of atoms is connected with the other group of atoms. And for this case, we do require the chemical shift values, and the value ranges from 0 to 200 ppm. ppm, as we said, parts per million. The number of the peaks in the spectrum indicates the number of the different carbon nuclei environments, and these environments can be identified by comparison with the values in the data book. So what do we mean by different environment? We said previously that when one element is bonded with the other element, then they are creating some sort of chemical environment for each other. Let's suppose if an element A is connected with an element B, then element A is becoming a source of chemical environment for B, and B is becoming chemical environment for A. If I connect another element C, then for C, both A and B are making a different chemical environment. For B, both A and C are making different chemical environment, and for A, the whole of the BC is making a different chemical environment. Or in other words, if I want to compare them, then both A and C have a different chemical environment from each other, because C is connected with B and A is connected with B and C. So this is how we say that different chemical environments are produced. Now here's a table for the chemical shift values. Just like in case of AS level, we had the values for the IR spectroscopy wave number. There we had the absorption range for the different groups of atoms. So in that case, we had the wave number values given in per centimeter for the absorption range. But here in A2, we have the chemical shift range represented by or symbolized by sigma, and the unit is ppm. So if a carbon, and all of these values are represented for the carbon-13, if a carbon is bonded with the is present within a methyl group, if it is present in the methyl group, or carbon is present within a CH2, or it is present in CH, in all of these cases, carbon will be having hybridization of sp3. Now, for this case, the pH, the chemical shift value will range from 0 to 50 ppm. In another case, if carbon is having hybridization of sp3, but it is present next to the alkene or arene, for example, this is carbon which is bold here. It is bolded here, but this carbon is bonded with a carbon-carbon double bond, which is considered as an alkene. And in this case, this bolded carbon is bonded with a benzene, having the three alternate double bonds. So for this case, the chemical shift value will be 25 to 50. Now here, sp3, for that carbon, which is next to the carbonyl or carboxyl group. Next to the carbonyl or carboxyl group. For here, this is the carbonyl group and this is the carboxylic group. So this carbon is bonded with next to carbonyl or carboxylic group. Its value is given. You will be provided this table in your exam. You just need to interpret these values for your given question. Now here sp3, which is bonded with the halogen, this sp3 bonded with the oxygen. So you can see here that the values are changing and they have some ranges over here. This is alkene. The carbon is a part of the alkene. So this is the part of the alkene. It is not like this one next to the alkene. Instead, it is with a part of the alkene or the part of the arene. So for this case, this is a range. And next sp2. And again, this sp2 is the one which is a part of the carboxylic group. So we have carbon double bonded O over here in both of these group of atoms. sp2 carbonyl, here it is aldehyde, this is ketone, so carbon of the part of the aldehyde and ketone, and this sp represents the hybridization of carbon, a part of the C double bond, triple bonded N. So this is how you need to use these values. Now, how we would interpret the structure of the compound? You just know that a compound in the form of the sample is placed in the strong magnetic field and that is exposed to the range of a different frequencies of the radio waves which will be absorbed. So some of the energy of different wavelengths will be absorbed and some will not be. Now that absorption of the range will be exhibited in the form of the peaks for in case of the NMR. So carbon-13 NMR is going to be discussed here, and that will give you the value of how many number of carbon atoms are present within the structure, within the molecule, within the compound. The peak values of carbon-13 NMR will indicate how many carbon atoms are there within the compound. Just like in AS, you had the formula of N is equal to 1.1 into 100 divided by the value was 13 into like this. So in this case, we have a different type of the formula. We don't have the formula, but we are going to interpret the number of the carbon atoms present in the molecule. So the reference or the standard value will be given by the tetramethylsilane TMS. The structure of this TMS is already discussed before. This is a TMS. Now its value will be indicated as a one small peak value on the TMS value of 0. This is TMS 0 and it increases left side and the value is reaching up to 220 ppm. Now one single peak over here of small intensity will indicate that this is TMS, tetramethylsilane, which is considered as a standard value here. Okay, now this is a table which indicates the chemical shift values of different carbon atoms which we have just seen in the table. Some carbon are part of the carboxylic group, some are next to the hydroxyl group. This is carbon bonded with the oxygen of a single oxygen atom. Now we are going to use the solvent. The solvent in this case will be the carbon-13 NMR analysis of CdCl3. This is a solvent. It is just like CHCl3. The difference is that they are using the next isotope of the hydrogen, which is hydrogen 2, having mass number of 2, represented by the symbol D, deuterium. The isotope 2 of the hydrogen, represented by D, is used here. Now, carbon-13 NMR is being used here before hydrogen NMR. The reason is that it is much simpler. We can interpret the carbon-13 NMR more easier as compared to the hydrogen NMR. The reason is that in hydrogen NMR, we have lots of hydrogen atoms, whereas carbon atoms are fewer than the hydrogen atoms, and more especially that they will be only one single lines of all the carbon atoms. That word is used here, singlets. That represents that one straight vertical lines are being used to indicate the carbon atoms, whereas in case of hydrogen atoms we have the the splitting of the single line. Even one single line is split into multi lines. So here's one such example which we're going to discuss here. We have carbon-13 spectrum of the ethanol. Now for this purpose you should draw the displayed formula. Now this is a displayed formula and we have two carbon atoms in this ethanol. One carbon is basically colored red and the other carbon is colored blue. In the same way, the NMR spectrum of this ethanol is given here. Now this A and B is colored blue and A is colored red. Now we have to decide what this spectrum is representing. So if we apply the carbon-13 NMR on this compound, then we will see that we have two carbon atoms. This red carbon atom is surrounded by OH group, two hydrogen atoms, and this whole methyl group. This is the chemical environment of this carbon, of red carbon atom. Whereas for the blue carbon atom, the environment for blue carbon atom are hydrogens, just like this carbon had also hydrogens, and then this whole molecule. This is the chemical environment for blue carbon atom. So you can see that the only difference which we see between these two carbon atoms is that for red carbon atom we have the OH group and methyl group, and for the blue carbon atom we have the CH2 group and OH group, but that is a far distant apart from the red one. Red one has directly connected, but blue one has indirectly connected, because for blue the first part is CH2 and then comes the OH. So that's how we have different carbon environments. On the basis of different carbon environments, we will have two different lines of carbon in the spectrum. We have now one line over here and second line over there, and this line, that should not be this much heighted, it should be around small value that indicates the TMS, that is clearly seen on the chemical shift value of 0 ppm. Now we have two lines. We have this one line representing one type of the carbon atom, and that B represents another type of the carbon atom. Now we have to match that which of these is represented over here. Although they are colored here, but we have to use the values from the table. So if we see here the value between 50 to 60 ppm value, that is basically for that carbon atom which is bonded with the oxygen. The carbon bonded with the oxygen directly over here must have a value between 15 to 60 ppm, which we can check from the table over here. So carbon next to the oxygen, this is a carbon hybridization, this is next to the oxygen. So we had C bonded with the OH. The ppm value is 50 to 70. This is the chemical shift value. This is a range which exactly matches with this range over here, 50 to 70 ppm. So this is the range 50 to 70. So that's why we have this carbon represented by A. So I can also write A over here. This peak of A is representing this carbon colored red. Now we can also confirm for the carbon represented by this second peak B. Now we can see that this carbon is bonded with the CH2 group. The blue carbon is bonded with the CH2 group. So it means we need to check for the carbon next to the CH2 group from the table. So carbon next to the CH2 group over here. This is the part. The carbon itself was sp3 hybridized. It was next to the, it could be said as next to the, or it could also be considered as the carbon of the alkyl itself. So carbon of the ethyl of the alkyl group itself is 0 to 50 ppm, because there is no such case in which carbon next to the alkyl group must be mentioned. So we consider them carbon which is a part of the alkyl group. So it is 0 to 50 ppm. So if we go back over here, we see that this peak value, chemical shift value of B, is present between 0 to 50 ppm. So between 0 to 50 is this one. That's why we will say that this is the carbon represented by peak B. So that's how we have identified that there are two carbon atoms and these are the chemical shift values. Now we can also check another example. Here we have an example of ketone with the formula of C5H10O. Although we can first we will provide it a molecular formula. They will not tell you whether it is ketone, aldehyde, or alcohol. They just give you the molecular formula. Now you can use this molecular formula to devise the formulas of aldehyde, ketone, and alcohol if it matches with this molecular formula. Let's suppose they have shown the ketone over here and not the aldehyde, because aldehyde and ketone both of them are the isomers of each other. Now over here, what do we have? This ketone matches with this spectrum. How do we know that? You can see if we look closely over here, we have in total three different types of the chemical environments. We have three different chemical carbon atoms. We can say we have three different chemical carbon atoms. Let's suppose if I start from the carbon which is colored green. Now for the carbon which is colored green, it has equal type of the groups on its either sides. It has CH2 group on this side, it has CH2 group on the other side. It has CH3 which is bonded with the CH2. It has CH3 which is bonded with the CH2. So both the sides of this carbon are equally the same. So that's why it is one type of the carbon atom. We now check for the carbon atoms which are colored purple, or you can say blue. So if I select this carbon, then it is bonded with the CH3 on this side, and it is bonded with the carbonyl group, CH2 group, and then CH3 group. In the same manner, if I go from this carbon, if I select from this carbon, it is connected with the CH3 on one side, CO, CH2, and CH3. So both carbon atoms are same. And in the same way, the red carbon atoms are also considered to be the same type of the carbons because they are connected with the same group of elements. So that's why we have in total three different carbon environments. We have three different chemical environments of the carbon atoms. So we say three carbon environments are there, or chemical environments are there, nuclear environments are there. You can use any word: nuclear environment, chemical environment, carbon environment. So that's why we have three different peaks over here: 1, 2, and 3 peaks. So this is a peak of this carbon, but one of the peak is present at the far left side of almost 200 ppm. Now the reason for this is that carbon is a part of the carbonyl group. So we go back to this table. This is better table to match these values. So when the carbon is sp2 hybridized and it is a part of the carbonyl group, then you can see that the values is around 190 to 220 ppm. So that's why one of the peak was at the extreme left side. Now what about the other? For the other two, I need to check one carbon which is a part of the alkyl group, the CH3 group, which is present in that compound. One of the carbon was part of the alkyl group, but the next was the part of the next to the carbonyl group. So you will take one carbon atom from this side and another carbon atom from this row next to the carbonyl group or carboxyl group, which had a 30 to 65 ppm. So 30 to 65 ppm and 0 to 50 ppm. You can see that it will end at 50 ppm, whereas it can exceed up to 65 ppm. So I will select the carbon which is exceeding the 50 ppm in this spectrum. So over here, the one which will exceeding the 50 ppm should be present over here. If it is not here, then we can still consider that one of the carbon is present at the extreme left side, which belongs to the carbonyl group. We'll have more better spectra over here to identify the structure compound. Now, another example is of the propane 1-ol and propane 2-ol. Now, for propane 1-ol, you can see that this hydroxyl group is bonded with the CH2. Now, it is present directly with the CH2, whereas it is present uh, indirectly, which means CH2 is a little far from the OH and CH3 is even more far from the OH. So in this way, on the basis of the distance from the OH group, all these three carbon atoms are chemically different from each other. That's why we have three different peak values. Now you have to identify which peak value belongs to which carbon atom. For this case, you need to check the values from the table. Now, for this purpose, I will go back. I need to check one carbon atom which is apart, which is next, which is bonded with the oxygen atom. We have already seen for the this peak in which we had the carbon, which was no, this was for the carbonyl group. Now this carbon which is next to the oxygen, I will check one carbon which is next to the oxygen, and this carbon which is bonded with the alkyl groups on either side, left and right side, and then this carbon is bonded again the alkyl group, but this will have a distance far from the oxygen. The carbon which is bonded directly with a highly electronegative oxygen atom, this is electronegative atom, it will have a value towards a more shielding value. It is more shielded over here. Now the carbon which is now a little far from the oxygen is present over here because it has smaller value than this one, and the rightmost carbon has in fact more distance from the oxygen. That's why its value is in fact even more closer to the zero value. So that's how we can find three different carbon atoms and their different positions. Although these two carbon atoms are considered to be chemically in the for these two carbon, you need to check the same column or the same row of the table, but even then you have to differentiate them because both are differentiated on the basis of the distance from the OH group. Now for this case, we have the carbon. This carbon, this is propane 2-ol. Now this carbon bonded directly with the OH. So that's why both of them have the values at the value above 60. I can confirm this from the table. The carbon which is bonded with the oxygen over here, the value is 50 to 70 ppm. So both of these structures have the value closer to the 65. So that's clear now. Now, in case of propane 2-ol, the two other carbon atoms are bonded directly with a CH. So that's why they have similar chemical environment, and they are all present. They both are present on a single chemical shift value because they have same chemical environment. But the height is different here. This height is almost 2 times the height of this carbon, which indicates that there must be two carbon atoms which are represented by this one single line, and this one single line representing only one carbon atom. So that's how we can differentiate these carbon atoms. Now another spectrum over here, we have to match this spectrum with the for the displayed formula given over here. We have three different structure formula, but we need to check which of this spectrum is matching with these three molecules. So that's an assignment. It's kind of small task to identify. So we will see if this is a molecular formula of the compound. Now it has one oxygen atom, and it could be aldehyde, it could be ketone, but the value of aldehyde and ketone is not present here. You can see from the table that if the carbon is a part of the aldehyde or carbonyl group, then the value should match 190 to 220 ppm. But that peak is not present in this case. That's why we will say that cannot be aldehyde or it cannot be ketone, which means we are left with other options which is only the alcohol over here. Now what we have here, if it is alcohol, we have three different arrangements. We can have propane 1-ol, we can have propane 2-ol, and then we can have the two. We have 1,2,2-dimethyl ethanol. So if we consider this type of the structure, then what we need to confirm from the graph, we have four different chemical environments in this case, and we need to check with the peak values over here. This small peak over here does not match with the carbon. Instead, that belongs to TMS, tetramethylserine. That's a standard value, so that's not a different chemical carbon atom. Why they are four different? Because this carbon is directly linked with this one. This carbon is bonded with the CH2 and then with the OH, which is farther from this carbon. This carbon is a distance of even more from the OH, and this carbon has more distance from the OH. So that's why all of these four carbon atoms are present at different distances from the OH. That's why they are all different chemical environments. So that cannot be this compound, because we have 1, 2, and 3 different lines present here. 3 different lines means 3 different chemical environments. But here we have 4 different chemical environments. They are 4. And over here we have 3 different chemical environments. So this could not be the compound. Now if we check this one, in this case, we again have 4 different chemical environments. How is it possible? This OH is bonded directly with this carbon, and this CH and these, they are not same. Why they are not same? Because this carbon is bonded with the CH3 group next to it, but this CH3 is not bonded with another carbon atom. That's why these two, blue and yellow, they are in chemically different environment. And the last one is definitely in a different chemical environment, which is bonded with the CH2, then CHOH, and they could only be of same environment with when they have same type of the group of atom on the either sides. So this cannot be the molecule. Now, if we check this arrangement of the of the alcohol molecule, then we can see that this carbon is directly bonded with the OH, and this carbon bonded with the CH2 and OH, whereas these two carbon atoms, they are directly linked with the same type of the arrangement of the molecules. Both of these carbon atoms on the either sides. So they are chemically same environments. So these two lines are being indicated over here by this large peak. So if I label over here, then these blue lines are representing this large line. The OH, this red carbon, that could be the carbon which is present towards a higher value. So this red carbon is present over here, and then this central carbon, that could be the over here, which I can denote by the purple line. So this central carbon is the central carbon over here. So that's how we can say that 3 different lines are being exhibited by this type of the structure of the molecule. Now another example, we have to tell this spectrum, which of these two molecules will give this type of the spectrum. This compound having an alkene and alcohol, or having only the aldehyde group. Now the peak at 203 ppm is due to the carbon in aldehyde or ketone. This large value, as we saw in the table, that could only be given by the carbon, which could be a part of the aldehyde. So that's now clearly shown here. The peaks at 37 and 6 ppm are due to carbon joined to another carbon by a single bond. So peak at 37 ppm, which is this value, this is 37 ppm. So this could be the because of the presence of the carbon which is bonded with the alkyl group. Now there are two such cases, but over here this carbon also bonded with the carbonyl. This is next to the carbonyl group. For this carbon we will say next to the carbonyl group. For this carbon we will say the part of the alkyl group only, alkyl. So this 37 ppm is basically this carbon. This carbon is 37 ppm, and this aldehyde carbon is this peak value. Now we are left with this only one carbon atom at the center. This interpretation fits with this, but not the. If the structure were CH2, if we deduce that, if we say if it is the second carbon, it is the second structure, then we would have be a peak in the range of the sigma 140 to 115 ppm, corresponding to carbon-carbon double bond, which does not lie here. There is no peak of 140 to 115 ppm, and a peak in the range of 75 to 55 pm, corresponding to carbon bonded with the OH group, which is also not here. Now another example here. This is a case of the propanone, which is a ketone. So two carbon atoms, they have the same type of the chemical environment that is represented by one large line, and this carbon is one bonded directly with the O. Sorry, now this carbon is one bonded directly with the O, so that could be this carbon atom. And these two carbon atoms, they are chemically same environment and they have smaller chemical shift value. That's why they are present on the this side. You do not have to consider this peak value, it is nothing. It's a slight mistake. Now these are some of the benzene compounds which indicates how symmetry is also there, or how different chemical environments are there in the case of the benzene. Be mindful that for benzene, all the carbon atoms are chemically same, because all of them are bonded with the hydrogen atoms and all of them have the carbon sp2 hybridization. So they all have single one value, and their peak is represented by one large vertical line. Now for this case, if we have two hydroxyl groups attached on uh, on adjacent carbon atoms, then in this case a planar symmetry can be constructed. This can give you chemical environments of three different types, because these one carbon atoms are those which are directly connected with the OH, so they are same. Now the other two carbon atoms which are connected with these carbon atoms, they are same. They are same carbon atoms, and these three are in fact more far from the OH, as though both of these three carbon atoms are same. So in total we have three different chemical environments. We say that these are three different chemical environments. Now over here, in this case, we have four different chemical environments, because the central carbon is different than the rest of the other carbon atoms represented by 2, 3, and 4. So we have four different chemical environments over here. You can clearly see that this OH is creating chemical environment differently on all of these carbon atoms, but these are same. These are same, 2, 2 are same, but 1 and 4 are different, because the distance of OH from 1 and for the O, they are different. And in this case, if we have the OH group on the opposite direction of the benzene, then they will create only two different chemical environment carbon atoms. We have 1, 1, 1, 1 carbon atoms, and then we have 2, 2, 2, which means all of these four carbon atoms are chemically of the same chemical environment. Now, some more example. Over here, we have the compound C6H5CH2 and CH3. Now, in total, we have 6, 7, 8 carbon atoms. But out of these 8 carbon atoms, if I draw the structure of this compound given by the molecular formula, it is like this: CH2 bonded with the CH3. Now, 6 carbon atoms which are present with the benzene ring, they are all of the same chemical environment. So they are all represented by this large line, but we can consider that one value of this carbon, that could be a different one, because it is connected directly with the CH2. So I can say this is carbon which is represented by this small value, since it is also considered next to the alkene part. Whereas these two carbon atoms, the CH2 carbon and the CH3. Now for this CH2, it could be this one, because it is closer to the carbon-carbon double bond of the benzene, and the other carbon, which is further from this carbon, could be this carbon, because it is in fact more at distance than the carbon than this carbon from the benzene structure. So that's how we can match the structures. And then the last example, in this case, we have in total 1, 2, 3, 4 different chemical environments of the carbon atoms. The carbon which is present with the which is as a part of the carboxylic group, that could be the carbon which is present at the far left side, because this is the carbon for which the chemical shift value matches with this one. So carbon 2 is this carbon 2. Now the value for the values are given in this paragraph. We can see that the peak on the left of the spectrum at 171 ppm is for carbon 2. That's what we have indicated. And the peak at 60 ppm is for carbon 3. 60 is carbon 3. This is carbon 3 over here, represented by this carbon. Now we are left with, why is it 3? Because 3 is present with the oxygen atom. We said for this type of the chemical shape, it is value ranges from 50 to 70 ppm. So that's why this is the carbon 3. Now we are left with these two peaks, which could be carbon number 4 and carbon number 1. We have to differentiate between them. Leaving the peaks, it is a little more difficult to assign the other two peaks at 13 12 22 ppm, but because the CH3 next to the carbonyl group, this is CH3 next to the carbonyl group, is likely to be more deshielded. More deshielded, having less shielding. More deshielded. It is more deshielded due to the electron withdrawing group effect of the carbonyl. We can identify carbon 1 with a peak at 22 ppm. So carbon 1 is over here, having, sorry, it has more shielding. Deshielded means having more chemical shift value. It has more chemical shift value. The one which is more deshielded has more chemical shift value. So the part of the which is next to the carbonyl group is given carbon number 1, and this is represented over here. This is carbon number 1. This is carbon number 1 having a value of 22 ppm. Leaving the peak at 13 ppm, this is 13 ppm over here, and that belongs to carbon number 4. So carbon number 4 over here belongs to this one because it is at a larger distance from the carboxylic group. So the one which is next to the carbonyl group is more deshielded, having more sigma value between these two. So that's why 22 was the one belonging to the carbon number 1. So that's how we have just completed the carbon-13 NMR spectroscopy. In our next class, we'll continue from the hydrogen or proton NMR spectroscopy, in which we'll consider the hydrogen 1 isotope only. Till then, take care and Allah Hafiz, friends.